I want to make sure we start the semester on the same page. So the first thing we're going to do is spend a little bit of time reviewing stuff from the first semester that we got to know here. I'm going to go over sort of the basics of how we represent organic structures, as well as some nomenclature basics. Hopefully get through some nomenclature basics because I really want to save all of Monday's lecture to review electron pushing arrows, to do mechanisms, all right? Might spill a little bit over, but yeah, that's the goal here. All right, so structures in organic chemistry. There are a few different ways to represent chemical structures. The first one that you learned about are what were called Lewis structures. And in a Lewis structure, every bond is explicitly drawn. Right? So for example, this would be the Lewis structure of propane. Okay. Another way, so in organic chemistry, we always care about the structure. I guess just to sort of put it first, the thing that we almost never use is what we would call the molecular formula. Right? This is something that you use in general chemistry, C3H8, that is completely insufficient in organic chemistry because many of the time that single molecular formula could correspond to many different organic molecules. It's just not enough information, right? So in organic chemistry, we always draw out the structure of molecules. All right, so again, we have our Lewis structure. That's kind of our most basic. All right, we also have a condensed structural formula. So for propane, this would be CH3, CH2, CH3. Also tells you the structure of that molecule in this kind of condensed way. I will say that these sort of things are most important to be able to read. Rarely do we actually sort of do our problems using these condensed structural formulas, but they fit in one line. So you see them in textbooks and in computer programs and stuff like that, right? So the important thing that we want to be able to do here is just to read these types of structures. Okay? But the real way we represent structures and how we're going to default in this course are what are called bond line structures. And sometimes they're called skeletal structures, but I call them bond line structures. And that is just using these zigzaggy lines, right? So this would be how we represent the molecule using these bond line structures. That same propane that we first represented in the Lewis structure, then the condensed structure. This one right here is the important one. We want to make sure that we know how to read these bond line structures. We're going to see these things over and over and over again. Okay? All right, so bond line structures. In a bond line structure, the two elements that are always present in an organic chemical, carbon and hydrogen, are implicit. They're just implied in that structure. They're not explicitly represented. Okay? So carbons are at all endpoints and intersections. So in my zigzaggy line, anytime I hit an endpoint or an intersection of two lines, there's a carbon atom. And then hydrogens. How do I know how many hydrogens there are on each carbon? Well, we just fill in to complete carbon's octet. Remember, how many bonds does carbon like to have? 4. So we look at how many are explicitly represented. All the rest of them must be filled in with hydrogens, right? So hydrogens fill in all remaining, or fill in, let's say, to complete carbon's octet. Okay. And then lastly, we have these things that may be in our molecule, what we call heteroatoms in organic chemistry. These are anything other than carbon and hydrogen. Those are explicitly drawn in. Those are explicitly represented with their chemical symbol. So heteroatoms and their hydrogens are not implicit but explicitly drawn. Okay? So let's make sure that we understand what the heck this is here. I'm going to draw a molecule using a bond line structure. And I need you to give me its molecular formula, aka tell me how many carbons and how many hydrogens we're looking at here. Okay, so this first one here, first of all, can anybody tell me what functional group we're looking at in that first molecule? Alkane, awesome. All right, functional groups are another thing that I want you to review. There's a review assignment, but there's something I'm going to completely leave to you. I'm not going to lecture on it. There is a posted video. It's also like a 3-second look up in a textbook kind of thing, so I don't want to waste class time on it. But we all want to be on the same page of what functional groups we need to recognize, right? So by looking at that molecule, I should know that it's an alkane. All right, how many carbons do we have? All right, let's go ahead. Carbons, we're going to label in, or we're going to color in orange here. And again, every end point and every intersection is a carbon atom, right? So indeed, I do have 6 carbon atoms in my molecular formula here, in my structure. All right, so the hydrogens are kind of the trickier part because I just have to fill in. If I look at, for example, this carbon here, how many hydrogens is it going to have? 3, right? It's already got 1 bond explicitly drawn to its neighboring carbon atom. That means to complete those 4 bonds it needs, we got to put 3 hydrogens. What about this one right here? How many hydrogens? 2. It's already got 2 bonds drawn, so it only needs 2. Same over here. These ones are also these terminal carbons, so they're going to need 3. And what about this guy in the middle? 1, right? It's got 3 bonds drawn. It still needs 4, so we got 1 more here. All right, so if we total it all up, we have 6 carbons and 14 hydrogens. hydrogens I did in red. Okay, cool. So now we have this second molecule here. What's my functional group on this molecule? Alcohol. So hopefully this is one that you can recognize. You haven't really talked about chemistry of alcohols, although you see them all the time in the lab because they're just such a go-to solvent. But this is actually one of the first functional groups we'll start out talking about. I lied, we start somewhere else. But we will get to alcohols here in the middle, all right? And what we can first notice of our alcohol is it's got to have that OH group. And those heteroatoms are explicitly represented, right? There's no implied hydrogen. You got to draw your hydrogen on those heteroatoms. But the carbons and their hydrogens are still implied, all right? So first of all, how many carbon atoms do we see here? We got 1, 2, 3. There is not one right here, right? That's where my oxygen lives. Cool, so we got 3 carbons. I think we can say pretty quickly that we have just 1 oxygen, because again, that's explicitly represented. Actually, just don't put the 1 in. All right, but what about how many hydrogens we have? Again, these are going to be implied on my carbon. So 1, 2, 3, 4, 5, 6, 7. Am I done? Don't forget this one as well, right? The one that was explicitly represented. So we have a total of 8 hydrogens in that structure. Okay? Cool. So basics of organic chemistry and how we're going to represent our molecules are using these bond line structures here. Again, you need to be able to count your carbon. You're going to hear me say this so many freaking times, it's not even funny, because it's the best double check that you can do when you do a problem. Count your carbons, right? So I'm going to go through, count your carbons at every endpoint and intersection, but then in your mind's eye, you also want to be able to fill in where those hydrogens are, right? By looking at how many bonds that carbon atom already has. Cool. All right. So we're going to move on now to things that we should be able to interpret from these bond line structures. What's called hybridization and related geometry. Okay? So it turns out that the shape of molecules, as well as the shape of their electronic structure, the hybridization, has a big impact on the reactivity of those molecules. One of the first functional groups you would have talked about reactions of are alkenes. And why are they so reactive? It's because of that sp2 hybridization. They got those p orbitals. Anyways, we need to review what the heck I mean by sp2 here, okay? All right, so let's just take an example molecule here. Going to be a big thing with a bunch of functional groups. I'm trying to make a point out of it. All right. So first thing we want to sort of define here is this concept of electron regions. These are bonds of any order or lone pairs. Okay, and this is going to be important because what we're going to do is count electron regions. And the number of electron regions is going to directly correspond to the hybridization of that atom, which in turn corresponds to its geometry. Okay. If an atom has only 2 electron regions, then it's sp hybridized, and it has a linear geometry. If it has 3 electron regions, it's sp2 hybridized, and it has a trigonal planar geometry. And lastly, if it has 4 electron regions, it's sp3 hybridized. Does anybody remember this geometry word here? Tetrahedral. Cool. All right, let's see if we can look at our molecule below. I want you to try to label all the sp2 hybridized, or I'm sorry, sp hybridized, sp2 hybridized, and sp3 hybridized carbons in that molecule. All right, and you got to do so by first counting the number of electron regions, because that directly points you to that. So first of all, let's just do this first one together. I have my carbon atom right here. It's got that one bond explicitly drawn. So what else do I know about that carbon atom in terms of its bonds? How many hydrogens does it have? 3. So it's got these 3 hydrogen atoms all around it. So now I need to look at that carbon and count how many electron regions it has. A bond of any order counts as 1, or a lone pair. All right, I got a bunch of single bonds, so I got a total of 1, 2, 3, 4 electron regions. And if I have 4 electron regions, what is the hybridization of that molecule, of that atom rather? sp3, right? So that particular carbon has this tetrahedral geometry. Okay, so again, see if you can't fill in. We got 1, 2, 3, 4 other carbons here. What are the hybridization of those 4 other carbons? All right, so all of these carbons that are fully decorated with 4 bonds would also be sp3 hybridized. Okay, we got 2 more to worry about here. This one and this one. Let's look here. Focusing on this carbon, I'm going to count the number of electron regions. Remember, a bond of any order is just 1 electron region. So even though it's a double bond, it's still only 1 electron region. And then this one, and then this one, bringing me to a total of 3. So if there are 3 electron regions, that means it's sp2 hybridized and has this trigonal planar geometry. Right? So that carbon atom, that oxygen atom, and its neighboring carbons are all in this flat geometry. Right, this trigonal planar geometry, and that really impacts how reactive that particular carbon is. Okay, lastly, and these carbons are really easy for people to forget, there is a carbon at the end of this triple bond here, right? It's triple bonded to the nitrogen on one side, and single bonded to the carbon on the other side. So there's a carbon here. How many electron regions does this carbon have? 2, right? This triple bond still just counts as 1 electron region, a bond of any order, plus the single bond on the other side. So indeed, this is an sp hybridized with a linear geometry. And you can see I drew my triple bond correctly because I drew it in that linear geometry, right? We got to draw our triple bonds with that linear geometry because that's the correct shape of that molecule. Cool. All right, so then the last thing with regard to structure we want to discuss is what's called formal charge. All right, we said that carbon likes to have 4 bonds. What do I mean by likes to have? It means that carbon is most stable when it has 4 bonds, which is when it has a formal charge of 0. All atoms are most stable when they have a formal charge of 0, right? And that's what we mean when we say it likes to have a certain number of bonds or lone pairs, okay? Well, cool. But super stable atoms aren't really always involved in chemical reactions. In fact, most of the time, there's some unstable intermediate that's actually propelling that reaction, okay? So we have these atoms that will adopt formal charges in our reactions, all right? So we're gonna make some cheat sheets here, okay? Let's start with oxygen, because this is one that we see quite a bit, and we're gonna make some categories here. Okay, we're going to make 4 columns. We're going to put our regular oxygen atom in the middle. Okay, and then we're going to tabulate how many bonds, how many lone pairs, and the formal charge. Okay, so oxygen, just like every other atom, is most stable when it has a formal charge of 0. When oxygen has a formal charge of 0, how many bonds does it have, and how many lone pairs does it have? All right, let's just go to our classic thing that hopefully we all have ingrained in our brain, our water molecule here. How many bonds does our oxygen have? 2. How many lone pairs does our oxygen have? 2. So oxygen is most stable, aka has a formal charge of 0 when it has 2 bonds and 2 lone pairs. Okay? Now, if I take one of those bonding pair of electrons and I put it directly on that oxygen atom, turning it from a bond into a lone pair, aka I'm going to decrease my number of bonds and increase my number of lone pairs. All right? So I guess just to draw that out, let's be good. Our most stable one has 2 bonds and 2 lone pairs. Now I'm going to look at an oxygen atom that has 1 bond and 3 lone pairs. Now it has more electron density sitting directly on that oxygen atom. So this doesn't have a formal charge of 0, but rather a formal charge of -1. All right, so if you see oxygen with just 1 bond and 3 lone pairs, that means it's holding a net negative charge. It's got a charge of -1. And then if we do the exact opposite, we turn one of those lone pairs into a bonding pair. So instead I'm going to increase the number of bonds and decrease the number of lone pairs. So for example, an oxygen with just 1 lone pair and 3 bonds, that would then have a formal charge of +1. A hydronium ion, for example, is an example of an oxygen with a formal charge of +1. It's got 3 bonds and 1 lone pair. All All right, so these are these patterns that we need to be able to spy here. All right, we're going to be taking electrons away from an atom and putting them on another atom. We need to tell what's going to happen to the charge when we do so. All right, so we're kind of boiling this down to these simple rules here that we can hopefully just spy. All right, so now we're going to play the same game, but we're going to do so with nitrogen. So we're going to create our same blank table here. And we're going to start out in the middle with nitrogen when it has a formal charge of 0. So how many bonds does nitrogen like to have? 3, and how many lone pairs? Just 1. So that is when nitrogen is its most stable, when it has 3 bonds and 1 lone pair. All right, by analogy of what we just did with oxygen, I want you to see if you can't fill in the rest of this table here. What would it look like when nitrogen has a formal charge of -1 or a formal charge of +1 in terms of the number of lone pairs and number of bonds? All right, again, based it on analogy of what we did with our oxygen atom. All right, so let's say that I turn one of these bonds into a lone pair. Is that going to increase or decrease my formal charge? All right, just like we saw here, if we go down in number of bonds and up in lone pairs, that will decrease our formal charge. So we're going to see the same pattern here. If instead I have 2 bonds and 2 lone pairs on my nitrogen, that nitrogen now has a charge of -1. That's just about the strongest base you can ever see. Nitrogen is super pissed when it has a negative charge. Not happy at all. All right, and then if we go the other direction, we start turning lone pairs into bonds. Now we increase in our number of bonds and we decrease in our number of lone pairs. Now we have nitrogen with a formal charge of +1. All right, so if nitrogen's got all 4 bonds, it's got a formal charge of +1. An ammonium ion is an example. All right, and then lastly, let's do the same thing for the star of the show here. We got our blank table, and we want to do carbon. When carbon has a formal charge of 0, we said it has 4 bonds and 0 lone pairs. All right, I want you to try to fill in, based on what we did previously, this row right here when carbon has a formal charge of -1, but then we're going to do this one together because it's a little bit weird. so again, anytime I turn a bond into a lone pair, go down in bonds and up in my lone pairs, that will decrease the formal charge, right? So this is a carbon that has only 3 bonds and 1 lone pair, meaning it's got this -1 formal charge, okay? Because it's carbon, we got some special names for this thing here. Remember, positively charged ions are called cations, negatively charged ions are called anions. So when it's carbon, we call it a carbanion. Okay? So now, if we look, like by analogy of what we did before, we were turning lone pairs into bonds. But I don't have any lone pairs to turn into bonds. Not only that, but saying carbon has 5 bonds is just ridiculous, right? I really hope I never see any structures drawn where carbon has 5 bonds, because that's like the fundamental rule of chemistry, all right? So a positively charged carbon is kind of a weird one. This is a carbon that has no lone pairs, but only has 3 bonds associated with it. Again, we got a fancy terminology for this thing. Because it's a positively charged carbon, this is what we call a carbocation. All right, hopefully this rings a bell from the future semester because it is a super important intermediate in a huge amount of reactions that we study in organic chemistry. Okay? The one thing about a carbocation that is so unique is if we've sort of calculated how many electrons a carbon has when it's neutral, or even a carbanion has, we would see that carbon has its full octet. It's got that full 8 electrons. A carbocation is carbon that does not have a full octet. And that's part of why it is so unstable and reactive, all right? So, carbocation, we just want to make note, has an incomplete octet. These carbocations are amazing at accepting electrons because of that, because they have these incomplete octets. All right? If we look above, the one thing that we want to note with regard to our octet for oxygens and nitrogens that's really important, kind of just a base rule that you know you're going in the wrong direction, is nitrogen and oxygen will never break their octet. You will never in your life see a nitrogen atom that has less than 8 electrons associated with it, right? If you draw that structure, you know something went wrong somewhere, okay? Carbon is the only one where we can violate its octet rule. Okay, so we just want to say always a complete octet. So yes, oxygen will adopt a positive charge, but it's not going to give up its electrons to do so. It still has 8 electrons associated with it. It still has that full octet. You're not going to ever wrestle away an octet from oxygen or nitrogen. Okay, carbon's kind of the only special one. All right, so then I'm going to draw an incomplete bond line structure here. And you're going to fill in any missing lone pairs and formal charges on those heteroatoms. We'll put a hydrogen on there. That's where we're going to see it. I see my oxygen, it's got these 3 bonds. How many lone pairs must it have? Because it has to have a complete octet. 1. And if oxygen has 3 bonds in 1 lone pair, what's its formal charge? Positive. I got my nitrogen here. How many bonds does that nitrogen have? 2. So then how many lone pairs must it have? 2. So then what's the formal charge on that nitrogen? Negative. Okay, and this is a great exercise. Truthfully, will this molecule ever exist? Hell no. That nitrogen's going to pluck that nitrogen right off that oxygen in a second, right? It wouldn't actually adopt this conformation, but it's good to be able to fill it. And that's kind of the point, is especially as you advance in organic chemistry, if you look at some more advanced organic chemistry texts, we get real lazy about drawing our lone pairs in there. And you just like your hydrogens, you got to be able to fill them in with your mind's eye, right? You just got to know if oxygen's got 2 bonds, it's got 2 lone pairs. If it's got 3 bonds, it's only got 1 lone pair and a formal charge, okay? All right, so we're just going to be able to sort of scratch the surface here, but let's go ahead and talk a little bit about nomenclature, and really we want to lay out our rules for how we go about assigning nomenclature. Let's put a simple example molecule over on the side. Okay. So whenever we do our nomenclature, we follow these sort of 4 steps here. 1, we're going to find our parent chain. And a parent chain is the longest continuous set of carbons. So I need to look at a molecule and I need to trace out what is the longest continuous set of carbons that I have. Okay. My parent chain here would be these 1, 2, 3, 4 carbons. You could have also said 1, 2, 3, 4, and you would eventually get the same name, right? That's fine because it's symmetric. But nonetheless, that longest continuous set of carbons is my parent chain. Okay. Let's remember we have these prefixes. Number of carbons. I think the first 4 are kind of the hardest to remember. Okay? 1 carbon has the prefix meth, 2 carbons is F, 3 carbons is prop, and 4 carbons is but. From then, they follow the, I think, Greek, whatever, the prefixes that we learned in geometry. Pent is 5, hex is 6, hept is one that people kind of forget, hept is 7. All right, if we want to complete our chart here. Eight is oct, 9 is non, I guess we can complete, 10 is dec. Okay, so we have these prefixes that we're going to use to name our parent chain, and we stick these prefixes on the suffix that corresponds to our particular functional group. In this case, we have an alkane, so that has this ane suffix. So if I got 4 carbon alkane as my parent chain, what would that parent chain name be? All right, so 4 carbons is but. Again, it's an alkane, so that's that ane ending. So this parent chain is butane. All right, cool. So my next step, and I'm going to leave some room because we'll fill in some more details here with another example next class. 2 is we're going to find and name our substituents. This is anything that points off of the parent chain. The entire goal of organic chemistry nomenclature is to account for every atom on that page, right? So in my butane parent chain, I got 4 of them down, those 4 carbons, but I'm still missing this one right here, and this would be considered a substituent. All right. Again, we're going to use our prefixes. There's 1 carbon in that substituent, so which prefix am I going to use? Meth, all right, and then we got endings here for our alkyl substituents. That prefix is, that suffix is YL. So this group right here with 1 carbon is a methyl group. Meth for 1 carbon, and then the YL because it's just carbons and hydrogens. All right, the next step is I need to number the parent chain. These numbers we call locants, all right? But yes, I need to number my parent chain. And I'm always going to do so in a way where I have the lowest possible numbers in my name. So what do I mean by that? Every parent chain can be numbered left to right or right to left, right? You can always number your parent chain one of 2 ways. So I'm just going to put them both down, all right? I'm going to go one way in blue, 1, 2, 3, 4. I'm going to go the other way in orange, 1, 2, 3, 4. And we got to decide which one of these numbering schemes is the correct number. Okay? And the important thing is when I get done with my name, I want the lowest possible number in there. So I'm looking at this methyl group right here. So should I pick, this methyl group right here. So am I going to pick the blue numbering scheme or the orange numbering scheme for that methyl group? Orange. I want it to be the lowest possible number. So absolutely, we're going to number in this direction here. So the locant of that methyl group is carbon 2. And then the last step is we're going to assemble our name. Okay, so we want locant, substituent, with the parent, and let's just make a note that there is no space between the substituent and the parent. In fact, there's really no spaces that will appear in your nomenclature until we get to certain specific functional groups. All right, you always run everything together. Okay, so for this one here, I have my parent chain is butane. I have a methyl group on carbon 2, so this would be 2-methyl butane. Run together, all one word. All right, and I've got every carbon accounted for in this name. I have my methyl carbon, my 4-carbon parent chain, my butane, and my location of that methyl group on carbon 2. All right, so for every seven, we'll sort of complicate things and add some special rules here, but anytime we do nomenclature, we follow these 4 steps. Find our parent chain, find and name our substituents, we got to number our parent chain, and then we put it all together at the end. Okay? Cool. All right, we're going to call it there. You have your practice assignments. They're not due until next week. I published everything that's going to be new next week so that you can kind of plan it out. Please make sure to sign up for that online homework system.